So now we're going to start section 4.2, which is about Rolle's theorem and the mean value theorem. So we're going to start with Rolle's theorem. And I'm going to write what it says, but then we're going to dissect it together. So Rolle's theorem says if you have let f be a continuous function on the interval a to b, and it needs to be differentiable on the open interval a to b. It says if f of a equals f of b, then there is at least one number c in the interval a to b such that f prime of c equals 0. So what's very important is your function needs to be continuous and it needs to be differentiable on your interval. And so let's dissect what this is telling us. It's saying that, let's visualize what's going on here. If f of a equals f of b, so when I plug in a, I get a y value. It has to be the same thing for b. And my function is continuous, so remember what continuous in terms of graphing means. You never pick up your pencil when you draw this graph. No matter what happens between these 2 points, there has to be a place where between them, between a and b, there has to be a c where the derivative, if I look at the derivative here, the slope of our tangent line, it would be 0. And so in this particular case, what this corresponds to for this picture is I have a relative maximum here. So at some point between a and b, my derivative has to be 0. Basically, because f of a equals f of b, my function goes up, it has to come back down. And so there's some point where the derivative stops being positive and starts being negative. So let's look at an example. Find the 2 x-intercepts of the function x squared minus 3x plus 2 and show that f prime of x equals 0 at some point between the 2 intercepts. So if I'm going to find the x-intercepts, remember that's where we set y equal to 0, and we factors into 2 and 1, and they're both going to be minuses. So I get x equals 1 and x equals 2. So those are correspond to my 2 intercepts. And if I plug in 1 into my function, and if I plug in 2 into my function, they both should output 0 because they're x-intercepts. So here f of 1 equals f of 2. And remember, to use Rolle's theorem, we need that our function is continuous. Well, remember our function f of x is a polynomial, so it's going to be guaranteed to be continuous and differentiable everywhere. But in particular, on the interval 1 to 2, since It is a polynomial. So I've got my two conditions for Rolle's theorem. My first condition said that my function needed to be continuous and differentiable. And my second condition said f of a has to equal f of b. So now I can say by Rolle's theorem, there exists at least one value c in the interval 1 to 2 such that f prime of c equals 0. So that's what we needed to show. Now if you want to find the specific value where the f prime of c equals 0, you're going to have to find the derivative of your function f. The derivative would be 2x minus 3. And if you solve for x, you'll get 3/2. So this is really our value of c that maybe we were looking for. C would be 3/2. So let's look at one more example here. Let's say f of x is the function x to the 4th minus 2x squared. And I want you to find all values of c in the interval -2 to 2 such that f prime of c equals 0. So again, I'm looking at a really nice function. I'm looking at a polynomial. So this function f is continuous and differentiable on the interval -2 to 2. If I plug in 2 into my function and -2, I get the same value back. I'm going to get 8. And so what this means, I meet both conditions of Rolle's theorem, so I can then use Rolle's theorem Rolle's theorem says that c exists, that I can find one of these values, and let's see if we can find them. So f prime, take the derivative of my function, it will be 4x cubed minus 4x. Set it equal to 0 and solve. I can factor out a 4 and an x out of both terms. So this factors into x minus 1, x plus 1. And I get 3 solutions. I get x equals 0, 1, and -1. So there was actually 3 values where the derivative was 0. Rolle's theorem only tells us that one value exists, but actually there are 3. And if you look at the graph of the function f of x, you'll see that the graph looks something like, has this shape here, has this like W kind of shape going on here. And so there are 3 places where the derivative is 0. If I look at the tangent line here, at -1, at 0, and at 1, all 3 of those, the slope of the tangent line is 0. So the derivative is 0 at those 3 places.